In the last video, we showed a 2 by 2 matrix. Then we took the inverse of that matrix and we showed how we can solve a series of equations simultaneously with that inverse matrix. Now, larger matrices like a 3 by 3 or 4 by 4, solving an inverse matrix by hand is a more involved process. We're going to show you how to do that here. In reality, you're most likely going to be using a computer program to invert matrices this large, or usually much larger. But understanding what the inverse of a matrix does and how it actually is applied is really important, so that you fundamentally understand what you want to tell the computer program to actually do. So let's walk through 3 of these different methods. This will be our example matrix A. We're going to try to solve for the inverse of this matrix, which will be this matrix here. Now remember, when we multiply the matrix by its inverse, as we show here, worked out here, we'll get the identity matrix. Remember, the reason that the inverse matrix is powerful is that when we multiply the matrix by the inverse, we get the identity matrix, and the identity matrix is represented as like the unit value 1. So the matrix and the inverse matrix act as reciprocals of each other. So as much as we can do multiplication in matrices, there's no division in matrices. So if you want to cancel something out, if you want to use a reciprocal of something, you use the inverse of the matrix. There are 3 methods that we're going to talk about today. The first method is basically the same method as the 2 by 2 method that we talked about in the previous video. Now, we didn't talk about this adjoint matrix A. What this adjoint matrix A is a manipulative form of the original matrix A. We did use it, but for a 3 by 3 matrix, it is a more involved process to find. So we're going to show how to actually solve for that. So we take the determinant of A, which we talked about in the last few videos, which is a scalar, and the reciprocal of that determinant, that scalar multiplied by this adjoint matrix A, gives us the matrix that is our inverse matrix. The second method is a linear row reduction. This method involves building a matrix with the original matrix A and your identity matrix. And the objective is to manipulate the different rows using these 3 rows and building equations relating them in such a way that the left side becomes the identity matrix. When we do that, the right side will then become the inverse matrix. And the third and final way we're going to use, the third way is programming, using computer programming. I particularly use MATLAB. A lot of my students use Python as well, but because I don't know exactly what you have access to, I will show you how to do this on Excel. Now, it's not the most efficient way, obviously. Using a dedicated computer program is preferred, but if you don't have access to one, especially if you're learning how to take inverse of matrices, this is a good way to check your work. And there's a few good functions that can help you understand whether or not you're solving these inverse matrices correctly using using Excel matrix tools. Now in the future, most of what you'll be doing will be done in computer programming, right? But if you're first learning how matrices work, how they interact with each other, it is good for these small scale matrices to solve them out by hand, right? That gives you a really good understanding of what it does, because when you're solving with computer programming, you might think, oh, why am I even wasting my time solving this by hand? But this becomes one small part of a larger problem, and you need to understand fully what each piece is doing, so that when you ask a computer program to do something for you, you know that you're asking it to do it in a correct way, or that when it gives you something that you don't believe is the right answer, that you have the intuition to really think about that. And that only comes from practice and working out the fundamentals and understanding the fundamentals. So that's the process we're going through right now. So let's take a look first at this first method. All right, so for the first method, what we need to determine first is the determinant of the matrix A, which we've done a few times now. Then we need to define what it means to take the adjoint or the adjunct of matrix A. And then once we have that, we have a scalar, which is 1 over the determinant A, and a matrix, a new matrix, the adjoint of matrix A. We multiply the scalar to the matrix, and we get our inverse matrix. So we're taking the determinant of a 3 by 3 matrix. So I'll walk through this a little bit, but I'm not going to go through every single step. You can work through this out yourself. So remember, when we take the determinant, we use vertical bars to represent that. That's what we're looking at. And there's a number of ways to do this, but I usually will just take a look at the top row, and whatever cell you're looking at, you basically cross out all columns, or that entire column and that entire row, and the values you're left with, that's your sub determinant. And then the signs swap, plus, minus, plus, minus, plus, minus, and so forth. But since we're selecting that first row, it's just going to be plus, minus, plus. So positive for this term, negative for this second term, positive for this third term. So I choose 4. So my subdeterminant will be 0, negative 1, 1, 1. For this one, this is choosing 2. So my subdeterminant values are 3, negative 1, 1, and 1, because I'm crossing out this top row and this column. If I choose 1, I'm going to choose these 4 values, 3, 0, 1, 1. And then once I have this form of the equation, then I take the 2 by 2 determinants, right? And remember, the 2 by 2 determinant is cross multiplying. So for this case, 3 times 1 minus 0 times 1. For this case, 3 times 1 minus negative 1 times 1, and so forth. And then you solve this, and we get our determinant as negative 1. We're going to use this determinant method over and over when we solve the adjunct. So how do we solve this matrix? We have our original matrix A. So the first step is to take the transpose of matrix A, right? Transpose means whatever row number it is becomes a column number. Whatever column number it was becomes a row number. So across the diagonals, that stays the same, because this is row 1, column 1. This is row 2, column 2. This is row 3, column 3. So swapping the row and column doesn't change. For this one, it does. So this is row 1, column 2. So I want it to be row 2, column 1. This is row 2, column 1, and it becomes row 1, column 2, and so forth. And so we do we take the transpose, denoting it with a superscript T, and then we find the cofactor. Some places will say find the cofactor and then take the transpose of it. All right, so this cofactor, this looks very messy. So let's focus on this section right here. First off, we have the designation of the sign right here. This is the same thing that we did when we checked the determinant. We have a plus, minus, plus. That's what we had here. Plus, minus, plus. And it just alternates. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, so this form is basically subbed through this system here. All right, what's in this matrix right here? This matrix is built, each term is replaced with the determinant. The determinant is the remaining components. So for this top cell here, that's this one here, I'm going to take the determinant of these values. For this, so 0, 1, negative 1, 1, that's what's shown here. For this cell here, I'm going to take the determinants of these values and these values. So 2, 1, 1, 1. For this determinant, I'm going to use these values, 2, 0, 1, -1. Something in the middle, like this value here, I'm crossing out that whole column and that whole row. So it's going to be 4, 1, 1, 1, and so forth. And then we take the determinant of each of these values, and that's what's figured out right here, utilizing the signs that are specified in this cell. So let's say I took 4, then these will be my determinant values here. Let's say I'm looking at this cell here, which would be, let's see, this one, right? So 4, 3, 2, 0, that's what's right there. Then I'll do cross multiply, 4 times 0, 3 times 2, and it's a positive sign, right? So I'll let you, if you want to check, go through each one. You can see that this is a bit of a tedious process. This is the exact same thing we did for the 2x2 case. It's just, it was a lot smaller, obviously. All right, so once we do that, we get our new matrix. Then, as the rule specifies up here, we take that new matrix and we divide, or we multiply that by the scalar 1 over the determinant, which we found was -1. And then we find our inverse matrix, right? So the elaborate process is finding the cofactor component to determine the adjoint or the adjunct of matrix A. Let's take a look at our second method. Okay, so for this second method, we're going to use linear row reduction. We're going to take our matrix A and the identity matrix, and we're going to try and manipulate this. And we can manipulate it by adding, subtracting, multiplying, or dividing the rows from each other and creating new rows. But whatever we do on one side, we'll do on the other side exactly the same way. And the objective, remember, is to change this left side to look like this. So we're going to want zeros everywhere except along the diagonal. So I'm going to do it in one method. It's probably not the most efficient method, but the way I'm thinking through it is where I'm trying to put 0 values and try to change certain values to a 1 value. So when I have a prime, that means I'm manipulating a certain row. So I'm manipulating this second row, and the way I'm going to do it is I'm going to add row 1 and row 2 from the original. So row 1 and row 2, this will allow me to force a 0 in the second row, third column, right? Which I'm trying to force. I'm trying to force 0, 0, 0, 1, 0 in the second row. So 4 plus 3 gives me 7, 2 plus 0 gives me 2, 1 minus 1 gives me 0, which I'm looking for. Then I get 1, 1, 0 on the right side. Okay, so next I want to force a 0 up here, right? Like I have in the identity matrix here. So R1 prime, this is R1 minus R3. So 4 minus 1 gives me 3, 2 minus 1 gives me 1, 1 minus 1 gives me my 0, then I get 1, 0, -1. Okay, let's see what I do here. I'm trying to get rid of this first value in my second row. So I say 7 times, so I have a 3 here and a 7 here. So I want 7 times this value minus 3 times this value, kind of like the common denominator thought process in fractions, right? So 7 times 3, 21, minus 3 times 7 is 21, gives me my 0. 7 times 1 is 7, minus 2 times 3 is 6, 7 minus 6 gives me 1. These are zeros, so this is going to stay as 0. It's good to force the zeros because once there are zeros, then you can utilize it in other rows and they're not going to have any effects. Then 7 times 1 minus 3 times 1 gives me 4. 7 times 0 minus 3 times 1 is minus 3. 7 times -1, -7 minus 0, right? So -7. So I got 0, 0. So this second row is pretty much done. And we can see that it's actually pretty much done because this matches the inverse matrix already. Okay, so next I want to get a 0 up in this first row, second column, right? So I go row 1 minus row 2. So 3 minus 0, 3. 1 minus 1, that gives me my 0. 0 minus 0, 0. 1 minus 4, negative 3. 0 minus negative 3 gives me positive 3. Negative 1 minus negative 7. 7 minus 1 is 6. Okay, looks good. This is pretty much done. It's scaled by 3, so I could divide by 3. So this divide by 3 gives me 1, negative 1, 1, 2, which matches what we have right here. So I just need one more step. I just need to get this last row right here. I have a 1, 1, 1. Well, I have a 1, 0, 0, 1. So I can combine all 3 rows together, and that'll get rid of these two, my first and second column of my third row. So I say row 3, this one, minus row 1 minus row 2. So that will give me my 0, 0, 1 right here. So what will give me here? Minus 4 minus negative 1 give me negative 3. Minus 3 is positive 3. Minus 1 will give me positive 2. Now this one is R3 minus R1 minus R2. So it's 1 plus 7 is 8. Minus 2 is 6. Right? And this matches our identity matrix. I think this method is a bit faster. But as we said, as your matrix grows larger and larger, we can use programming methods. So let's take a look at some functions that Excel gives us that we can use. We can utilize the two methods to solve for 3x3, 4x4, maybe even a 5x5 matrix. But once we get larger than 5x5 matrix, if you try to solve these matrices by hand, most likely you'll make a mistake. It's going to take you a lot of time to solve for it. So in most cases, we use programming languages. I personally use MATLAB. A lot of my students use Python. Excel is pretty accessible, and it does have some pretty good matrix functions. So if you remember, if you've used Excel, Excel is a spreadsheet program. So you can type values into basically a grid, and then you could ask it to do something with these values, right? So here, your columns are designated by letters. Your rows are designated by numbers. So up here, I type in my matrix A, 4, 2, 1, 3, 0, negative 1, 1, 1, 1. That's what I just type in, right? So if you have Excel, you can type that in directly. Then I go to cell A5, so column A, row 5. Go to the cell. I type in equal sign, and then you can type in a function. You can tell it what to do. I want M for matrix inverse, and then you need to tell it what to invert, right? So you open parentheses, A1 colon C3 close parentheses. What this is saying is I want from A1 to C3. A1's right here, C3 is right here. So it's calling this matrix. Instead, you can click and drag, and you can select these cells to tell it to type this in. All right, once you hit enter, it should populate this matrix right here. This matrix right here, as you can see, is your inverse matrix. Negative 1, 1, 2, 4, negative 3, negative 7, negative 3, 2, 6. You can see here. Now there's a number of other call functions that Excel can use. You can transpose, you can get the determinant, or you can even check that this is the correct matrix, inverted matrix, right? MULT is matrix multiplication. It calls for two sets of matrices. The first one right here, A1 is C3, that's this one right here. And the second one, in this case, the inverse. And it will output what should be your identity matrix. As you can see, the values are not exactly, it should say 1, 0, 0, 0, 1, 0, 0, 0, 1. Here it's not exactly 0, but these values, 10 to the negative 16, 10 to the negative 16, are very, very small. So a lot of times programming languages, depending on the functions they use to solve things, there's rounding errors. It doesn't have the ability to have infinite amount of significant figures. So depending on what it does and where it's rounding, you're going to have some rounding errors. So values that should be 0 may just show up as very, very small values. Values that should be infinite may show up just as very, very large values, right? So when we're looking at larger matrices, you're going to want to know how to use a programming language to solve for them. When you're solving things like that, you also are going to still want to, in the back of your mind, know what inverting matrices are actually used for, so that when you're calling for it, it's usually in the scope of a larger problem. You're usually not just solving it just to solve that mathematical problem. We'll start looking at examples of these larger problems so that we can see how solving a series of equations simultaneously is effective and used. And then we'll start looking at other means of interacting vectors and matrices together for more engineering physical systems.